Well, hi everybody. In this screencast, we're going to take a look at two kinds of limits, limits at infinity and limits that are infinity. We'll take a look at limits that are at infinity as x gets larger and larger, and limits that are at a particular value of x, but the values of the function get larger and larger and larger, and that's why we say these are limits involving infinity. So let's talk definitionally, and I'll hit you with a definition that you should probably be aware of. I won't make you memorize a definition because that would be crazy, but you should at least see it. So we say that the limit as x approaches infinity of f of x is some number L if. Now, let's talk about what that means. So I've got some function, maybe it is this function. This is the function f of x is 2x minus 5 over x minus 3. There's a vertical asymptote at 3, a horizontal asymptote at 2. And I want to say that the limit as x approaches infinity of f of x is 2. Why? Because as I go further and further out, as x values get larger and larger and larger, this function gets closer and closer to 2. I want to say that that is true. And that is a nice handyman's definition for what it means for a limit at infinity to be L. The further out we go with the x values, the closer this function gets to 2. There's a rigorous definition. I will show it to you. It says that for every epsilon greater than 0, there exists some number capital M such that for all x, if x is bigger than M, then the absolute value of f of x minus L is less than epsilon. So what does that mean? I want to show that the limit is 2. So I put an epsilon band around 2. This is 2 plus epsilon. This is 2 minus epsilon. It's an epsilon band, a band of length epsilon, of radius epsilon around 2. Is there an x value after which the function is always within the band? And it turns out that this is the place where that happens. That's capital M. And even if I were to make the epsilon band smaller, I'd just go a little bit further out and find an M, the place after which the function is within the band. And that will happen for all values of epsilon. If I make epsilon very, very small, it doesn't matter. I just trace further and further out, and the further out I trace, I will find an M, I promise. There's a similar definition for what happens with a limit as x approaches negative infinity. Is there a value after which the function is within the band, stays within the band, and that would happen from there. Okay? Okay. But really, what are we talking about? As x gets bigger and bigger, as x gets closer and closer to infinity, what is happening to these values? Well, this is getting really big and that doesn't really matter. This is getting really big and that doesn't really matter. So from an algebraic standpoint, what we usually do is we say, if I'm interested in this, let's just divide everybody by the highest power of x. And the highest power of x is, in fact, x. And we divide everybody by the highest power of x. And we ask, what happens as x gets really, really big? Well, as x gets really, really big, this stays 2, it's unaffected. This stays 1, it's unaffected. And these go to 0. 5 over x, bigger and bigger denominator means the fraction goes to 0. 3 over x, the denominator gets bigger and bigger and bigger, so the fraction goes to 0. These guys go away. And I'm left with 2 over 1, and that's 2. That's the way the algebra traditionally works out. So, everybody's favorite game, find them. Oh, wow. I didn't know that. Find them. Great. So we will find some limits. If I'm interested in the limit as x approaches infinity of x plus 512 over x cubed minus 6x minus 100. You might think about that for a moment. And then the limit as x approaches negative infinity of 4x squared plus 6x plus 12 over 5x squared plus x plus 3. We could think about that for a moment. And so just based off the ideas we were talking about, if we were to divide everybody by the highest power of x, well, if we divide everybody by the highest power of x, the highest power of x is x cubed. So you get this. Everybody gets divided by the highest power of x. What happens to all of those as x gets large? Well, these are all 0. And you're left with 0 over 1. That's 0. From which we draw a more broad conclusion. If I'm taking a limit at infinity and the power, the degree of the denominator is greater than the degree of the numerator, you're going to go to 0 every time. 80% of the time, this works every time. By contrast, if we divide everybody by the highest power of x here, the highest power of x here is x squared. So we divide everybody by x squared. Oh, that is horribly sloppy. So sorry about that, folks at home. Divide everybody by the highest power of x. What happens? These are all 0, and we're left with 4 over 5. From which we draw the more broad conclusion that if the powers in the numerator and the denominator, the degree of the numerator and the degree of the denominator are the same, just compare their coefficients. And this helps us do things like this. Find all horizontal asymptotes for y equals radical 4x squared plus 9 over 3x plus 1. All horizontal asymptotes. Well, horizontal asymptotes, to find those, we take the limit at infinity and we take the limit at negative infinity. Sometimes they're the same, sometimes they're not. Let's take limits at infinity and negative infinity and see what happens. So you've got the limit as x approaches infinity of this. Well, what is that? Well, I've got powers of x. Let's divide everybody by the highest power of x. Now, you would think that x squared is the highest power of x, but that's not true because you're taking a square root. And when you take a square root of x squared, that's just x. So we're going to divide everybody by x. Not so bad in the denominator, little tricky in the numerator. We'll divide in the numerator by the square root of x squared. And I'll ask myself, what happens as x gets large? Oh, sorry, forgot the limit. The limit of this is the limit of this. That's very important. So as x gets bigger and bigger and bigger, this drops out, and you're left with the square root of 4 over 3. So y equals 2/3 is a horizontal asymptote. Well, what happens as x gets larger and larger in a negative direction? Well, as x gets larger and larger in a negative direction, what are we essentially working with here? We've basically got this in the numerator, and we've basically got that in the denominator, because we've pretty much figured out that these guys are useless to us. They're really not doing anything for us. So what ends up happening? Well, these terms are all positive, because we're taking square roots of large positive numbers. But these values are all negative. And since they're all negative, we're still approaching 2/3, but the Well, we're approaching negative 2/3 because these are all negative and these are all positive. So we can take a look at whether we're approaching positive infinity or negative infinity and make some determinations. Are we approaching positive 2/3 or negative 2/3? And the answer is in fact yes. Okay, one other thing to consider before I hit the second screencast. If I'm looking for horizontal asymptotes for this thing, it is helpful for us to think about what this is. When we go ahead and, oh, that's not what I want. When we go ahead and find this limit, remember what 3 to the negative x is? And what 7 to the negative x is? When we go ahead and figure this out, x gets bigger and bigger. I think we know what's in play. But when we play this game, think about what's happening as x gets larger and larger in a negative direction. Think about what's happening to this and then what's happening to that. You might be very surprised at how this all plays out. That's a nice little something to think about. Hit the pause button and think about it. Okay, if you hit the pause button and thought about it, as x gets bigger and bigger, these guys drop out. We're left with 2/5. But as x gets larger and larger in a negative direction, these drop out. These pop up here, and we're left with 3/7. So there are two horizontal asymptotes. One is here, and the other is here. That's a very interesting question. Okay, so we'll talk about vertical asymptotes in a moment, because this is already too long.